My name is Mark Manning, and I'm here to present the topic of tunnel boring machines, or TBMs. In this presentation, I will first provide a breakdown of the different types of TBMs that are currently in use, including some of the trade-offs that need to be considered when selecting the right TBM for the job, and I will also explain the different types of components that make up a TBM. I will then introduce a couple of machines that represent the state-of-the-art in TBM design and explain how they're being used. My focus will then turn towards performing a detailed analysis of the earth pressure balance tunnel boring machine. I'll look at the importance of maintaining the earth pressure balance and explain how this is accomplished in terms of what variables the designer or operator must control. I will then explain what ground settlement or ground losses are and what dangers they cause on surrounding infrastructure. Lastly, I will discuss my computer simulation that I created using MATLAB to demonstrate the range of motion of TBMs with active articulation, and I'll explain my method of position tracking that I used in my model. The design of a TBM can be quite complicated and can vary depending on the type of design, but I tried to provide a simplified diagram showing several of the main components of a TBM. At the heart of the TBM is the cutter head, which is mounted with many small cutting wheels and scrapers, and contains openings for the material to be drawn through the machine, where it can be drawn away by the conveyance system. The cutter head is driven by electric motors and pushed forward by a series of hydraulic cylinders that surround the TBM. These are commonly known as the thrust cylinders. The entire assembly is then surrounded by the shield wall. Many TBMs also have a robotic method of installing a concrete lining to construct the walls of the tunnel while drilling. There are two main types of TBMs, hard rock TBMs and soft ground TBMs. The two categories are based on whether the ground is hard and stable enough to support its own weight, or if the soil is softer or looser, the TBM will be responsible for supporting the weight of the ground above it. The hard rock TBMs are available in both single shield or double shield designs, where the double shield design has two sets of hydraulic actuators that are used along with a hydraulic gripper. The soft ground TBMs differ in the method used for providing face support to counteract the ground pressure. The two main types of soft ground TBMs are the earth pressure balance design, that uses a buildup of excavated material to create a back pressure to support the face, and the slurry pressure balance design, that adds compressed air and the cutting fluid bentonite in the cutting chamber to balance this pressure. I will now introduce a couple of the state-of-the-art TBM designs, the first being an example of a hard rock tunnel boring machine. The Haraneck double shield hard rock TBM uses a pair of gripper shoes in between two sets of hydraulic cylinders. These grippers hold onto the tunnel walls while excavating, and then retract to move forward, allowing more room for the rear thrust cylinders to force the cement lining into place. The gripper shoe design is only possible for hard rock TBMs, where the tunnel walls are strong enough for the grippers to provide sufficient torque and longitudinal forces to the cutter head. Here is another example of a soft ground TBM that uses the earth pressure balance shield design. The Robbins Company Earth Pressure Balance TBM works in soft grounds to cut soil and mix it with cutting fluids or foams to turn it into a muck-like consistency. This muck fills the back of the cutter head to equalize the external earth pressure. The excavated material is then easily transported out of the tunnel by a screw conveyor. The pressure balance is maintained by controlling the rate of advance of the TBM and the material removal rate of the screw conveyor. To give a bit more detailed explanation of the earth pressure balance design, I found this diagram rather useful. As you can see, there are two elements to the earth pressure: the weight of the earth itself, seen measured from the street level, and the pressure caused by the water weight, measured in relation to the groundwater table. The amount of face support required is then found by summing these pressures and adding some margin for error. If the earth pressure placed on the TBM is not properly supported, it will cause ground settlement or ground losses, which is when the ground shifts and moves to be drawn towards the tunnel, and this is a very serious issue since any buildings or infrastructure that are nearby can be seriously damaged. Although ground losses occur most often at the face of the cutter head, they may also occur at the shield of the TBM or at the tail end if the tunnel lining that was installed isn't properly supporting the ground around it. Here's an example of the devastating impact that ground settlement can have. This event took place in Cologne, Germany, and led to the loss of 2 lives. The collapse occurred after the tunnel had already been installed, and groundwater movements also played a role in this event. but this event still may have occurred due to the instability of the soil left after the excavation process. The design that I used for my MATLAB simulation was a double-shielded earth pressure boundary TBM with active articulation. The design has two sets of hydraulic cylinders, where the thrust cylinders provide all the cutting force, and the articulating cylinders allow the TBM to twist its way around corners. My simulation was a simplified version of this design, which focused on using the inputs of the velocity of the thrust cylinders, the angle of the articulating cutter head, and the direction in which the cutter head is angled, since the articulation is able to adjust both the pitch and the yaw. Here's a brief video that demonstrates the effectiveness of this design and the very tight turning radii that this design is capable of. The design separates the forward thrust motion using a secondary set of articulating cylinders to move the cutter head from side to side. Before creating position tracking simulation using an extended Kalman filter design, research was first done to see how positioning information is commonly gathered by TBMs. Without GPS, underground position tracking can prove to be quite difficult. A method of underground surveying was found to be quite effective at tracking the TBM's position. The total station, labeled 1, aims at a reference prism, labeled 9, that is at a known position. The total station then aims at a pair of motorized prisms, labeled 6, mounted on the TBM to compute with the laser range data to find the position of the TBM. It was assumed that with the surveying occurring from the back of the TBM, the coordinate system used in the kinematic model needed to also be located at the back, in the center of the rear shield. For developing a controllable design, a coordinate reference frame could also be placed at the front of the TBM to incorporate the joint velocities of the articulating cylinders into another kinematic model centered around the front of the TBM. In order to provide an accurately positioned reference prism, it takes quite a bit of surveying and requires the triangulation of all the known points along the TBM's path where access to information from the surface is possible. A method called zigzag traversing is used to relay the position information from the surface along the reference prisms that are placed at equal intervals to the total station. I'll now present the results of my kinematic model with position tracking using an extended Kalman filter. The kinematic model was tested using a set of inputs for the velocity and joint angles to demonstrate a helical path. The plot shown on the top represents a bird's eye view, and the plot on the bottom is a side view to show the depth of the TBM as it spirals downwards. The position plot shows the position of the coordinate system based around the rear shield. The kinematic model was derived from the coordinate transformation using the ZYX Euler angles for yaw, pitch, and roll in relation to the fixed reference frame. This simulation is sped up. In reality, the TBM would move much slower, and I could have used a step input to demonstrate the time to retract the thrust cylinders. The model was able to verify the desired motion could be generated based on the kinematics of the TBM, and that the position could be tracked very accurately, assuming that the position information could be gathered by the surveying system that was mentioned earlier. The orientation of the TBM was also found to be tracked rather accurately with the use of the extended Kalman filter. This concludes my presentation on the tunnel boring machine. Thank you for listening.